Introduction to Statistics, Chapter 5, Probability, Section 5.3, Independence and the Multiplication Rule. Two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. An example, if you draw two cards from a standard deck of cards and replace the first card before drawing a second card, the draw of the second card is independent from the draw of the first card because the first card plays no effect on the second card because you put it back in the deck. Now, two events E and F are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So looking back at our example, if you draw two cards from a standard deck of cards, but this time do not replace the first card before drawing the second card. The draw of the second card is dependent on the draw of the first card. There's going to be one less card in the deck, and there's going to be whatever card you drew, one less of those in the deck. So the first draw will affect the second draw. So these are dependent. Multiplication rule for independent events. If E and F are independent events, then the probability of E and F is equal to the probability of E times the probability of F. An example, suppose the events E and F are independent. Probability of E is 0.3, probability of F is 0.6. What is the probability of E and F? Well, in this case, the probability of E and F would be the probability of E times the probability of F, which is 0.3 times 0.6, which turns out to be 0.18. Now, if we take this to a word problem, about 13% of the population is left-handed. If two people are randomly selected, what is the probability that both are left-handed? So we look at this, probability 2 left. That's going to be the probability the first one's left times the probability the second one's left, which is going to be 0.13 times 0.13, which is 0.0169. Now, do you understand why the draw of the two people would be independent? Would the first person you draw have any effect on the second person? No. So these would be independent events. Now, multiplication rule for n independent events. What if we have more than two events? So you'd have E1, E2, E3 all the way down to En, and they're independent events. Then the probability of E1 and E2 and E3 and En would be the probability of E1 times probability of E2 times probability of E3 all the way down to probability of E sub n. So let's look at this. An example. Suppose you roll a fair-sided die 4 times. What is the probability of rolling 4 sixes? First, do you understand that each roll is independent? The first roll would not affect the second, would not affect the third, etc. So the rolls are independent. So we can use this rule for independent events. So the probability 4 sixes, that's going to be the probability the first one's a 6 times the probability the second one's a 6 times the probability the third one's a 6 times the probability the fourth one is a 6. Well, the probability that you get a 6 is 1/6. So this is going to be 1/6 times 1/6 times 1/6 times 1/6, and use your calculator. You would end up with that answer in red. Now, example 2. About 13% of the population is left-handed. If 3 people are randomly selected, what is the probability that all 3 are left-handed? Again, we start off probability 3 left. That's going to be the probability the first person's left times the probability the second one's left times the probability the third one's left. Well, each one is 13%, which is 0.13. Multiply it together, and you end up with 0.002197. Right, now, computing at least one probability. Probability at least 1. That's going to be easily done by taking 1 minus the probability of none. So let's look at a couple examples. Let's go back to rolling the 6-sided die 4 times. What is the probability of rolling at least 1 6? In other words, I could have 1 6, I could have 2 6s, 3, or all 4 6s. I just want the probability at least 1 6. So the probability of not 6, we need to understand this. Well, the probability of rolling a 6 is 1/6. The probability of not 6 is 5/6. Now I need to understand what's the probability no 6s out of the 4. That's the probability of none. So no 6s out of 4, that would be 5/6 times 5/6 times 5/6 times 5/6. You know, the first one's not a 6, second one's not a 6, third one's not, fourth one's not a 6. And I left this as a fraction, 625 over 1296. You could have put it as a decimal, it wouldn't matter. But now let's get to the question. The question is probability at least 1/6. Well, that's going to be 1 minus the probability no 6s. All right, so we just figured out no 6s was 625 over 1296. So we take 1 minus that, use your calculator, you'll get 0.517746914. And of course, they'll ask you to round it so many decimal places. Now let's go back to the left-handed people. About 13% of the population is left-handed. If 3 people are randomly selected, what is the probability that at least one is left-handed? So we want to do this 1 minus none are left-handed. So first we have to figure out what's it mean to be not left-handed. So the probability not left-handed, well, if 13% are left-handed, that leaves us with 87% not left-handed. So not left-handed is 0.87. So probability no left out of 3. So the first one's not left, second one's not left, third one's not left, so that's 0.87, 0.87 times 0.87, which turned out to be 0.658503. Now, the probability at least one left is going to be 1 minus the probability no left. Well, we just calculated probability no left out of the 3. So we take 1 minus the 0.658503, and you end up with 0.341497. Now, here's a situation where if you look at that answer, 0.341497, you know, you might not think it makes a whole lot of sense. But remember, probability can be thought of as a percent, a decimal, or a fraction. So 0.341497 actually would be 34.1%. So does 34.1% make more sense than 0.34? For a lot of people it does. So understand that probability can be thought of as percent or decimal. All right, and this brings us to the end of section 5.3, a very short, sweet section.